Welcome to Lecture 21, in which we will begin to talk about flip-flops. The first flip-flop we'll talk about is the D flip-flop, and the input-output table for the D flip-flop is as shown here. I'll explain this input-output table in just a moment, but let's go ahead and look at the symbol for the positive edge triggered D flip-flop. There are two frequently encountered symbols for this device. One would be like this. And another would be like this. Notice that the only difference between these two is that over here on the second one we have this bubble, and both of the outputs are labeled Q, but then we have the bubble to invert this second output, whereas over here we just have Q and Q complement. And in both cases the top input is D. Don't want that to look like a P. Let's well, just didn't do that too well. Now, so in both cases the top input is D, and then we have a clock labeled C. And now let's look at this and try to understand what it means. Well, over here on the output side, these pluses mean the next value of Q. And so we see that the next value of the output in some cases will depend on the present value. So the next value of Q can in some cases depend on the present value of Q. Now in these two cases it does not, but in these two cases it does. And likewise, it's important to notice here what's going on with the inputs. What this says is the following. When we have an input, when the input D is equal to 0, when the clock goes from 0 to 1, this is the positive edge. So when or some people call it the rising edge. So when the clock transitions from 0 to 1, and only at that instant, what will happen is the flip-flop will basically, at that moment, it will look at the D, what's available at the D input, and if that is a 0, then the next value of Q will be 0, and the next value of Q complement will be 1. On the other hand, if at that moment when the clock goes from 0 to 1, if there's a 1 input at D, then the next value of the output will be 1, and the next value of Q complement will be 0. And what the last two lines in this input-output table say is that if C is constant and equal to 0, it doesn't matter what we do with D. We can switch the D input back and forth as many times as we wish. As long as C stays at 0, nothing will happen on the output. The next value of Q will remain as the present value of Q, and the next value of Q complement will remain as the present value of Q complement. And likewise, as long as the clock is constant and equal to 1, it doesn't matter what we do with D. We can switch it back and forth as much as we want. We still have the next value of Q is equal to the present value of Q. The next value of Q complement is the present value of Q complement. And if we wished, we could actually put in, now it's not traditional to do this, but we could actually, if you wish, we could put in two more lines in this input-output table, and those two would look like this. Sorry. Well, no, this is correct. Actually, though, I should say here. There. And what these last two lines say, for this one right here, this says that if at a moment when the clock goes from 1 to 0, if the input D is 0, the next value of Q will be the present value of Q, and the next value of Q complement will be the present value of Q complement. Or if at a moment when the clock goes from 1 to 0, if D is 1, the same thing will be the case. So the only thing that the only time when anything will happen here is when the clock is going from 0 to 1. Otherwise, in all the other cases, the next value of Q is the present value of Q, next value of Q complement is the present value of Q complement. It's only for the positive edge triggered D flip-flop, it's only in these two cases that anything will change over here for the output. And likewise, for the negative edge triggered D flip-flop, what would happen then is that we would have Q here and here, Q complement here, and down here we would have a 0 and a 1. So this is, let's just go ahead and note, this is for the positive, and I'll put or rising edge triggered D flip-flop. And so that's basically all we have. One last thing to note is that it's an easy way to remember this is that think of the D as representing the word delay. In other words, when D is 0, this output will be like a delayed version of that. In other words, as if D is 0, then as soon as you get a positive edge to the clock, then that output will be 0. And when the D input is 1, as soon as you get a positive edge trigger, then or positive edge to the clock signal, then you'll get a 1 for the output. So if you remember the word delay, and it will help you to remember this entire table. And then the only other thing you need to keep in mind is whether it's a positive edge trigger D flip-flop or a negative or falling, it's also called a falling edge triggered D flip-flop. But this is how the D flip-flop works. And now let's look at another kind of D flip-flop. Another kind of flip-flop. The T flip-flop is perhaps a little bit more interesting than the D flip-flop. Its input-output table looks like this, and the symbols we use in circuits to represent T flip-flop are shown here on the right. And this is similar to the situation we had before, since we're talking here about a positive edge triggered T flip-flop. we can see here in the last 4 lines of this input-output table that nothing happens if the clock is constant equal to 0. And by nothing happening, let me make sure it's clear what I mean. I mean that the next value of Q just remains equal to the present value of Q, and the next value of Q complement remains equal to the present value of Q complement. And that will be the case in all 4 of these final situations. So in other words, as long as the clock is constant, whether it's constant and equal to 0 or constant and equal to 1, as long as the clock is not changing, then nothing happens to the output. Likewise, if the clock is changing from 1 to 0, if it has a trailing or negative edge, in either one of those cases, nothing will happen to the output of a positive edge triggered T flip-flop. The only time that we will have any possible change in the output of a positive edge triggered T flip-flop is when the clock has a positive edge. In other words, when it goes from 0 to 1. And what happens with the T flip-flop is different from what happens with the D flip-flop. Remember that for the D flip-flop, for those 2 cases, the next value of the output was just a delayed version of D. So when D was equal to 0, the next value of the output was 0, and when D was equal to 1, the next value of the output was equal to 1. We see that right up here, 0, 0, and 1, and 1. But for the T flip-flop, it's different. For the T flip-flop, if T is equal to 0, then the next value of the output is equal to the present value of the output, and the next value of the complement is the present value of the complement. But what is interesting is when T is equal to 1, and in that case, the next value of Q is equal to the present value of Q complement, and the next value of Q complement is the present value of Q. So just as we could think of the D for the D flip-flop as representing the word delay, we can think of the T in the T flip-flop as representing the word toggle. In other words, when T is equal to 1, when it's activated, then whenever we see a positive edge, it will toggle the output. So if the output is currently 0, it'll be a 1. If it's currently 1, it'll go to 0. So that's the way that the T flip-flop works. And now let's look at some exercises to reinforce our understanding of how the D flip-flop and the T flip-flop work. Let's now look at a couple of examples to reinforce what we've been talking about. Here in this first example, we have a clock signal, and it will just about always be the case that the clock will be a regular pulse train like this. Notice that it goes up from 0 to 1, from a value of 0 to a value of 1 at time t equals 0, and then at 1 it goes down from 1 to 0, and it for one time increment it stays at 1, one time increment it stays at 0, one time increment at 1, one time increment at 0, and so forth. And that will be the same for both of the examples that we'll look at here. But in the first case, we're going to be looking at a D flip-flop, and we'll consider this to be a positive edge triggered D flip-flop first, and then we'll see what differences it would have made if it were a negative edge triggered. And it is important that we know what the original value, or some people call it initial value, what is the initial value of the output, and then we are being challenged to fill out the rest, the output for the rest of these times. So let's see how this would go. And actually, for edge-triggered flip-flops, this is extremely easy, because all you have to do is to identify the edges at which transitions can occur. Now remember, if this is a positive edge-triggered flip-flop, then the only time that we can have a change in the output is when the clock has a positive edge. And so if we look here at this clock in this first example, it has a positive edge at 0, a positive edge at 2, a positive edge at 4, a positive edge at 6, 8, and 10. Let me go over that one more time. Now remember, a positive edge is when the value of the signal goes from 0 to 1. Some people call it a rising edge. And the only times it has a rising edge from 0 to 1 are at 0, 2, 4, 6, 8, and 10. Now it has a negative edge or a trailing edge at 1, 3, 5, 7, 9, and 11. So we'll get to that in a moment. But right now we're talking about a positive edge triggered D flip-flop, and it's only going to look at the value of D at those times when the clock has a positive edge. So let's see what happens. Now remember, for a D flip-flop, the next value of Q will always be determined by the present value of D at the moment of the triggering. So at the moment of this first triggering event, the first positive edge, D is equal to 1. And therefore, at that moment, the output Q is going to go to 1. So we'll make this change here. We'll keep that. We'll extend this from 0 to 1, and then flatten out that part of the curve there. So this is to reflect that the output goes from 0 to 1 at this first positive edge, and the reason for that is that at that first positive edge, D is equal to 1, and therefore the output will change to reflect that. Now, since there's nothing else going on with this flip-flop, we can immediately extend this line all the way over here to just before time t equals 2. Why? Because there are no more positive edges. If we look here at the clock signal, there are no more positive edges. After we look at this positive edge at 0, there are no more positive edges until we get to 2. And so we know immediately that we can just extend this line. Now, once we get to this next positive edge at 2, we look at the D signal, and this time it's equal to 0. And we know that when D is equal to 0 at the triggering event, then the next value of Q will be 0. So now we need to go back down to 0. And now we'll go ahead and extend that to just before the next positive edge, which is at 4. And at this next positive edge of 4, we see that D is equal to 0. And of course, so that means that the next value of Q should be 0. And the previous value of Q is also 0. So we just keep on here at the 0 level. And we extend over here all the way until just before 6, because that's the next positive edge. At this next positive edge, D is equal to 1, and therefore Q will switch up to 1. And then we can extend that all the way over here to just before 8. At the because 8 is the next positive edge. At this positive edge, D is equal to 1, so the next value of Q will be 1, just as is the present value. So we keep on here at 1. We extend it all the way to just before 10. At 10, D is 1 again, and so we can extend it, and that would be the value, the plot for the output Q for a positive edge triggered D flip-flop if D and C are given as shown here. Now, on your test questions, I'll go ahead and look ahead to that. I give a clock signal, and I give an X here, which will in some cases refer to D, and in some cases it will refer to T. You can see in the first two problems, X is regarded as the D input of a positive edge triggered D flip-flop, or the D input of a negative edge triggered D flip-flop, and then in 21.3, X is regarded as the T input of a positive edge triggered T flip-flop. So the test problems are extremely similar to the problem that we've just done. But what you're asking these problems is to identify all the times at which Q will change from 0 to 1. That's the question in 21.1, in 21.2, and also in 21.3. So if that had been the question here in the problem that we just did, in this problem here that we just did, if the question had been to list all of the times at which the output will change from 0 to 1, then you should list time 0 and time 6. Those would be the two times at which the output would change from 0 to 1. At 0 and at 6. Now, let's redo this same problem, but with the assumption that we have a negative edge triggered D flip-flop rather than a positive edge triggered D flip-flop. So we'll go ahead and erase everything we just did there. And now we're going to redo this now, but assume this is a negative edge triggered D flip-flop. Well, since this is negative edge triggered, that means that we only need to look at what's happening at times t equals 1, 3, 5, 7, 9, and 11, because those are the times when the clock has a negative edge. So let's go ahead and extend this all the way to just before 1. And we see that at the first negative edge, D is equal to 1. So we will do this. At the next negative edge, which is at t equals 3, D is equal to 0. So at that negative edge, we'll go back down to 0. At the next negative edge, which is 5, D is equal to 1. So we need to go back up to 1. And at the next negative edge, here at 7, D is equal to 0. So we'll go back down to 0 at that negative edge. Now extending this over to the next negative edge, which is at 9. At that negative edge, D is still 0. I shouldn't say still 0, because actually it has gone up to 1 in between times, but that makes no difference at all because there was no negative edges in there. So anyway, at 9, at t equals 9, D is equal to 0, and therefore Q will stay at 0. And here at the last negative edge, D is equal to 1, so Q will change to 1. And this would be the appropriate graph for the output if this were a negative edge triggered D flip-flop. And so again, if you were posed with the question of identifying the times at which Q goes from 0 to 1, in this case, the answer would be at t equals 1, and t equals 5, and t equals 11. So I hope that clarifies how the D flip-flop works. And now we'll look at the T flip-flop. And again, in our first example, we'll assume that it's a positive edge triggered T flip-flop, and then we'll also look at what would happen if it were a negative edge triggered T flip-flop. So now that you've seen how it goes with the D flip-flop, I hope that you'll, before we do this together, I hope you'll try it on your own first, and then come back and we can do it all together. Okay. So now we're ready to look at the first case here, where the assumption is that this is a positive edge triggered T flip-flop. And since the assumption is positive edge triggering, we only need to look at what's going on at C equals 0, 2, 4, 6, 8, and 10. So let's see. At the first positive edge, here at 0, T is equal to 1. And when t is equal to 1, that tells us that we need to toggle the output. So the output will go from 0 to 1 at t equals 0. Now, at the next positive edge, which is 2, t is equal to 0, and if t is equal to 0, there's no toggling that occurs, so we continue with an output of 1. When we go over here to the next positive edge at 4, t is still equal to 0, well, t is equal to 0, and so again, no toggling occurs, and the output remains at 1. At the next positive edge of the clock signal, which is at 6, t is equal to 1. This tells us we need to toggle the output, so it will go from 1 down to 0. We extend this just before the next positive edge, which is at 8, and at that positive edge, t is equal to 1, so we will toggle again. And here at the last positive edge, which is 10, t is equal to 1, so we will toggle once again. And this would be the output for a positive edge triggered T flip-flop. And if you were asked to identify the times at which the output would go from 0 to 1, it would do that at time t equals 0, and also at t equals 8. And now, as a final example, let's redo this one, but assume that it is a negative edge triggered T flip-flop, and I definitely hope that you'll try this on your own. First, and then we'll all do it together. Okay, so now for our final example, we're now considering this to be a negative edge triggered T flip-flop, and so that being the case, we want to look at the negative edges of the clock signal, which is at t equals 1, 3, 5, 7, 9, and 11. At this first negative edge, t is equal to 1, so we toggle the output. At the next negative edge here, t is equal to 0, so there's no change in the output. At the next negative edge, which is at t equals 5, t is equal to which is at t for time is equal to 5. The t input is equal to 1, so we need to toggle again. So we'll go from 1 back down to 0. The next negative edge, the t input is 0, so there's no toggling in that case. We stay at 0. At the next negative edge, again, the t input is 0, so again there's no toggling. And finally, at the final negative edge, which is at the time 11, the t input is equal to 1, so we want to toggle there. And this would be the output in this case. And if you were asked in this case to identify the times at which the output goes from 0 to 1, it would be at time 1 and also at time 11. So that's how you'll do problems of this nature. And so now you've already been given a preview, but just to go over this one more time. So the test problems for this lecture all refer to the diagram shown here, which is very similar to what we were just doing. And I've started off, I say that the initial value of Q is 0, and then you're supposed to take it from there. And in 21.1 we assume that X is the D input of a positive edge triggered D flip-flop, and you're supposed to list all the times at which Q will change from 0 to 1. In 21.2, assume X is the D input of a negative edge triggered D flip-flop and list all the times at which Q will change from 0 to 1. And then finally, in 21.3, if you assume X is the T input of a positive edge triggered T flip-flop and list all the times at which Q will change from 0 to 1. And then 21.4 will be based on that same diagram, but it will be given in class. So that concludes Lecture 21, and good luck.